Hello everyone. In this video, you will learn how Mohr circle is used in geotechnical engineering, particularly in the analysis of the shear strength of soil. Before watching this video, I strongly recommend that you go through the previous video in this series, where I discussed two-dimensional stress analysis, stress transformation, and Mohr circle. Understanding those concepts will make it much easier to you to follow the materials that are presented here. You will find the link of that video in the description below. It is also available in the I button above. Now, this is one 2D stress element. Now, for a geotechnical problem, compressive stress is normally taken as positive. So, sigma x, sigma y, these are actually normal compressive stress. So, it will be taken as positive. So, sigma x, sigma y both are actually positive. And this is the direction of positive shear stress. This is the direction of positive shear stress. The logic of this positive shear stress is discussed in detail in the previous video, but again I am repeating it in short. Actually, for this particular phase, if we think, this particular phase is actually positive phase, because if we draw one normal over this particular phase, then that normal will actually on the positive y direction. So this is actually positive phase. And if we think for this phase, if we draw normal over this particular phase, then that normal will be also positive. That normal will be also positive because this is along the positive x direction. So normal over both this plane are actually along the positive x direction and along the positive y direction. So both these planes are actually positive. So this is the plane of x because the normal is along x direction. So for the positive x plane, the direction of shear stress will be along the positive y direction. And this is the positive y plane because the normal is along the positive y direction. So for positive y plane, the direction of shear stress will be also along the positive x direction. So this is the logic. And this is the negative plane of y. If we draw one normal over this particular plane, the normal will be along the negative y direction. So this is the negative plane of y. Here the direction of shear stress will be along negative x direction. Negative plane, so negative direction. Again, if we think for this particular phase, this is actually the negative plane of x. If we draw the normal will be along the negative x direction. So this is the negative plane of x. So for negative plane of x, shear stress will be along the negative y direction. So this will be the direction. So this will be the direction. We have to remember that this is actually the nature of shear stress when the condition is positive. When the condition is positive. These two are actually the horizontal plane. For horizontal plane, shear stress will actually create some clockwise rotation. And for the vertical plane, these two are the vertical plane. For vertical plane actually, the shear stress will create some anti-clockwise rotation. And these two shear stress are actually numerically equal. One is tau xy, then another is also tau xy. This is tau xy, this will be also tau xy. Actually, by definition, one is tau xy, another is tau yx. But mathematically, both will be same. So we will, for every problem, we will actually use tau xy. For both the shear stress, we will use tau xy. And mathematically, both are actually same. The values are same. These two shear stress are known as complementary shear stress. How tau xy is equal to tau yx, that I have discussed in the previous video. But here actually, we will use the value of tau xy. So this is the thing. Now, we have to calculate the normal and shear stress for this inclined plane. Now again, one thing we have to remember that when we will consider the inclined plane, normally the angle will be taken with respect to the horizontal plane. With respect to the horizontal plane, we have to consider the angle, and this angle will be theta. And over this plane, we have to measure the normal stress, sigma n, and the shear stress, tau nt. So this is the normal stress, this is the shear stress. Why you are using the term tau nt? N is the normal, T is the tangent, normal and tangent. Now sigma n is acting on the normal direction of the plane, and the shear stress is acting along the tangential direction. So that's why you are saying this is tau nt. First one is the plane, normal plane, and tangential is the direction. The direction of the shear stress is along the tangent. So first is the plane, second is the direction. That's why we are saying this is tau nt. and normal stress is sigma n. So sigma n and tau nt we have to calculate the value. Now these are the equations for calculating the normal stress and shear stress. For a particular condition of normal and shear stress, if sigma x, for a particular condition of sigma x, sigma y and tau xy, if all these values are given, then for any particular angle, then for any particular value of theta, we can calculate the normal and shear stress by using these two equations. By using these two equations, we can calculate the normal and shear stress for any particular angle. The angle can be anything from 0 degree to 90 degree. The value of theta can be anything. Now one thing we have to remember, actually these equations are very similar with the equation of normal and shear stress that are used in the problem of solid mechanics. Like in the previous video what I have discussed, there is some difference in the equation. Very minor difference, but that we have to know, that we have to remember. Actually for the previous video, for any problem related to solid mechanics, in any book of solid mechanics, you will get that the equation of normal stress is something like this. But these two equations are not same. This pair of equation and this pair of equation is not same. What is the difference? There are only two differences that we have to remember. Actually for the first equation, for the equation of sigma n, the only difference is that for the solid mechanics problem, it was sigma x minus sigma y. Sigma x minus sigma y by 2. But here actually it will be sigma y minus sigma x by 2. That we have to remember. This is very important. Sigma y minus sigma x by 2. This difference is due to when you will go for any problem related to solid mechanics, at that time normal stress are normally considered tensile. Positive normal stress means tensile. But here actually positive normal stress is actually compressive. So this is actually the difference in the sign convention. So for that reason there is some difference. And one thing is also very important, that for soil mechanics problem, normally the vertical stress sigma v is actually greater than the horizontal stress. Sigma y will be normally greater than sigma x. So this equation is actually, for that reason also we can say that as sigma y is greater than sigma x, so this equation will actually change. This equation will actually change. You have to remember this, that for the problem of geotechnical engineering, sigma y will be greater than sigma x. Because for most of the real life problem, horizontal stress is little bit less than the vertical stress. Vertical stress is more than the horizontal stress for most of the geotechnical problem. Not for all type of case, but for most of the case, vertical stress is little bit more than the horizontal stress. And for that reason, sigma y minus sigma x is considered. For the second equation, another thing we have to remember, it will be sigma y minus sigma x by 2 again. For solid mechanics problem, it was sigma x minus sigma y by 2. Again here actually it is sigma y minus sigma x by 2. But here actually for the shear stress, the sign convention will be different. Here actually it is minus and plus. For the geotechnical problem it will be plus, second one will be minus. Just the opposite. So this is plus and this is minus. So that we have to remember. These two are the difference. So one difference is, again I am repeating, in place of sigma x minus sigma y, for geotechnical problem it will be sigma y minus sigma x. And for shear stress equation actually it will be, first one will be plus, second one will be minus. Just the opposite of the previous case, opposite of the problem related to solid mechanics. So this is the difference. So these two equations you have to remember. Now we will construct the Mohr circle. For Mohr circle, normal stress will be along the positive x direction and shear stress will be along the positive y direction. Positive shear stress will be along the upward direction. Negative shear stress will be along the downward direction. So this is again one thing that is actually opposite. For solid mechanics problem, what we have considered the positive tau as along the downward direction. But here actually we will consider the positive tau along the upward direction. So this is one another thing that is actually different. So first we have to take these 2 points for constructing the Mohr circle. This point is actually the point corresponding to the vertical plane. If we consider one particular small 2D element, then for the vertical plane, the normal stress will be sigma x and the shear stress will be tau xy. Now for this point, this is sigma x tau xy. Now sigma x is obviously positive. because for this type of problem we are saying that compressive stress will be positive. So sigma x is obviously positive, and tau xy is actually creating some anti-clockwise moment. And this type of shear stress will actually create the anti-clockwise rotation, and anti-clockwise moment will be actually positive. So this point is actually sigma x tau xy. Now the second point, this point is actually point corresponding to the horizontal plane. For horizontal plane, the normal stress is sigma y and the shear stress is tau xy. It looks like this. Now here actually this particular shear stress is actually creating one clockwise rotation, and we are considering that anti-clockwise rotation is positive. So here actually the clockwise rotation will be actually negative. So this particular plane, this particular point is actually sigma y minus tau xy. One is sigma x plus tau xy. Sigma x positive because it is compressive. Tau xy positive because this particular set of shear stress is creating anti-clockwise movement. So it is positive. For the horizontal plane, sigma y is positive because it is compressive, but tau xy is actually creating clockwise movement. So it will be negative. So the second point is actually sigma y minus tau xy. So these are the 2 points. One corresponding to the sigma x is corresponding to the vertical plane. This is for the vertical plane, and this is for the horizontal plane. These two are the stress. Now after we put these 2 points, we have to connect these 2 points. And when we will connect these 2 points, it will cut in this particular point. And obviously the coordinate of this particular point will be actually the average of these 2 points because it is in the midpoint. So for the first point, the coordinate is sigma x tau xy. For second point, it is sigma y minus tau xy. So for the center point, for this particular central point, this is actually the midpoint of these 2 points. So it will be sigma x plus sigma y by 2, and tau xy plus minus tau xy by 2. So it will be 0. So this is the midpoint. Now taking this point as the midpoint and taking this particular distance as the radius of the Mohr circle, we will draw the Mohr circle. We will draw the Mohr circle. So this will be our Mohr circle. This will be our Mohr circle. And this will be the radius of the Mohr circle. This will be the radius of the Mohr circle. How it is coming? This is very simple. This is actually very simple. How this is coming? One point is this sigma x tau xy. Another point is this sigma y minus tau xy. Their distance is actually the diameter of the Mohr circle. The diameter of the Mohr circle is actually the distance between these 2 points. So how much is the diameter? Diameter is this. Diameter is this. So this is actually this is the diameter of the Mohr circle. So if we just half it, if we just take the half of this value, then it will be the radius of the Mohr circle. So if we take half, then this 2 value will go inside the square root. So finally it will become like this. So this will become the radius of the Mohr circle. So this is the value of radius of the Mohr circle. Now this is another concept which is also very important. Like if we think for the horizontal plane, this plane, for the horizontal plane actually, the stress is sigma y and tau xy. Sorry, this is the direction, sigma y tau xy. Sigma y tau xy. So this is the stress, this point is actually the stress, this point is the point corresponding to the horizontal plane. Now when we measure the theta, when we measure the direction of a particular inclined plane, always we measure with respect to the horizontal plane. For geotechnical problem, for any type of geotechnical problem, we will measure the theta with respect to the horizontal plane. So this particular plane is very important. Horizontal plane is very important. So with respect to this point, we have to rotate the point, we have to move the point by an angle of 2 theta if we want to get the stress for a particular angle of theta. In real life, if the angle is theta, in Mohr circle it will be double, it will be 2 theta. So if we want to calculate the stress for a plane which is at an angle of theta in the real life problem, then in Mohr-Circle we have to rotate the angle by 2 theta. And for this particular plane, we will get the value of normal and shear stress. If we just rotate the value by 2 theta, then from this particular point, from the value of, suppose this is for this point, if we measure the normal stress, this will be the normal stress and this will be the shear stress. So if we measure the coordinate of this particular point, then actually we will get the value of normal stress and shear stress. Normal stress and shear stress for the point which is at an angle of theta. Now if in place of theta the value is suppose theta 2, then we have to rotate this particular point, we have to rotate this line by an angle of 2 theta 2. So that is the concept. For every change in the value of theta, we have to rotate this particular point by an angle of 2 theta. And when we will measure the angle and when we will measure the coordinate of that particular point, from that coordinate we will actually get the value of normal and shear stress for that particular inclined plane. Now these are the 2 points corresponding to the major principal stress and minor principal stress. Because if we take any point over this particular Mohr-Circle, we can consider any point over the particular Mohr-Circle. For this point actually normal stress will be maximum. Because over this particular Mohr-Circle, anywhere if we go, this point is actually the rightmost point. For this point actually sigma is the maximum. So this point is the point of maximum normal stress, which we consider, which we say as major principal stress. Major principal stress is actually the point of maximum normal stress. In Mohr-Circle, it is the rightmost point. For this point, normal stress is maximum. And again, the same thing, that if we look for the whole Mohr-Circle, for this particular point is actually normal stress is minimum. For this point, normal stress is maximum. For this point, normal stress is minimum. And this point, we say this is actually the point of minor principal stress. This point is the point with minor principal stress. So leftmost point is the minor principal stress with the minimum value of normal stress, and rightmost point is the major principal stress with the maximum value of normal stress. This is the rightmost point, this is the leftmost point. And for these 2 points, another thing is very important. For these 2 points, shear stress is actually 0, because these points are over the x-axis. These 2 points are actually over the x-axis, that is the axis of sigma. So for these 2 points, the value of tau is actually 0. So for major principal stress and minor principal stress, their condition, these planes are actually known as principal plane. The plane with major and minor principal stress, that planes are actually known as principal plane. For principal plane, shear stress will be 0. When the stress is major principal stress or minor principal stress, for that condition, shear stress will be 0. And what will be the value of major principal stress and minor principal stress? That is also very simple actually. We know the value of radius of Mohr-Circle. This is the radius of Mohr-Circle. This is the value, radius of Mohr-Circle. Now we know the coordinate for the center of Mohr-Circle. We know the coordinate for the center of Mohr-Circle. We know that the coordinate is sigma x plus sigma y by 2 0. So from origin, the value of sigma for this particular point, the center of the Mohr-Circle, this value is actually sigma x plus sigma y by 2. So how much will be the minor principal stress? Minor principal stress will be sigma x plus sigma y by 2 minus r. It will be minus r. Then we will get the minor principal stress. For major principal stress, it will be sigma x plus sigma y by 2 plus r. If we just add the value of r, then it will be major principal stress. So r is actually root sigma x minus sigma y by 2 square plus tau xy square. So this is the value of minor principal stress, and this will be the value of major principal stress. So this will be the value. From Mohr-Circle actually we will get the, if we just draw the Mohr-Circle, by measuring these 2 values we can actually calculate that how much is the major principal stress and how much is the minor principal stress. Now actually with respect to the horizontal plane, again I am repeating that this particular stress is actually the stress corresponding to the horizontal plane. the angle between the horizontal plane and the major principal stress, the major principal plane, that angle will be actually theta p1 in the real life. That means if we just draw the 2D stress condition, this is sigma y and this is tau xy, the stress corresponding to the horizontal plane. If we just take this angle as theta p1, then for this particular plane, the stress will be the principal stress, major principal stress. So it will be sigma p1. Shear stress will be 0, so we do not have to consider it. So with respect to the, we are measuring with respect to this point. We are measuring with respect to the horizontal point, not with respect to the vertical point. We are measuring the value with respect to the horizontal point. So with horizontal plane, the angle of the major principal stress, the angle will be theta p1. In Mohr circle, it will be double to theta p1, but in real life, it will be theta p1. Over this particular plane, we will get the major principal stress. And theta p2 for the minor principal stress. That means this will be the plane with the angle theta p2. Over this particular plane, actually, we will get the minor principal stress. Over this particular plane, we will get the major principal stress. Over this particular plane, we will get the minor principal stress. And actually the angle, the difference between 2 theta p2 and 2 theta p1, this gap is actually 180 degree. This gap in Mohr circle, the gap is actually 180 degree. So in real life, theta p2 and theta p1, the gap will be 90 degree. So the plane of major principal stress and the plane of minor principal stress, these planes are actually perpendicular to each other. So the plane with major and the plane with minor principal stress, these two planes will be actually perpendicular to each other. Now these are the 2 points corresponding to the maximum shear stress and minimum shear stress. This point is corresponding to the maximum shear stress because for this point tau is maximum numerically. For this point tau is actually minimum. This is the value of maximum tau, this is the value of minimum tau. So actually one is plus, another is minus, but both are actually maximum tau. The sign is actually different, but if it is plus 55, it will be minus 55. So mathematically the value will be equal, but the sign will be different. So again one thing you can actually see here, that actually the value of maximum or minimum shear stress, that value is actually the value of radius of the Mohr circle. So already we know the equation of radius of Mohr circle, or we can say actually this gap is actually the gap of sigma 1 minus sigma 2, because this is sigma 2 and this is sigma 1. So the diameter of the Mohr circle is actually sigma 1 minus sigma 2. So the radius of Mohr circle is actually sigma 1 minus sigma 2 by 2. This value is actually the maximum value of shear stress. So maximum tau max is actually sigma 1 minus sigma 2 by 2. So for these 2 points, we will get the maximum and minimum value of shear stress. And for these 2 points, actually, that sigma value will be sigma average, because the x value for the central point, the center of the Mohr circle, and for this point with maximum shear, for both these 2 points, sigma is actually same. So for the condition of maximum shear also, the normal stress will be sigma x plus sigma y by 2. And shear stress will be tau max, which is actually sigma 1 minus sigma 2 by 2. So this is the coordinate of the point with the maximum shear. Now again, with respect to the horizontal plane, the plane of maximum shear, its angle is actually theta s1. Theta s1 is actually the angle of plane of maximum shear with respect to the horizontal plane. And the plane of minimum shear, that angle is actually theta s2. Theta s2. With respect to this point, if we just measure the angle, in Mohr circle it will be double. Obviously in Mohr circle it will be double. In Mohr circle we will get the value of 2 theta s1 and 2 theta s2. From these 2 value we can actually get the angle of maximum shear plane and minimum shear plane. Now one thing is very important. Now what I have discussed till now, that thing I have discussed in the previous video also. in details. In the previous video also I have discussed all that thing. But this particular thing is very important for soil mechanics. This thing is the concept of pole. This is very important for determining the failure plane. Now, double angle approach I have already discussed that this particular stress condition, this is the stress corresponding to the horizontal plane, and this is the stress corresponding to the vertical plane. This is for the horizontal plane, this is for the vertical plane. Now, if you want to calculate the stress for one particular plane which is at an angle of theta with respect to the horizontal plane, if this angle is theta, if we want to calculate the stress for this particular inclined plane, then we have to rotate this point in the anti-clockwise direction by 2 theta. Suppose this is the horizontal plane, we want to calculate the normal and shear stress for a plane which is at an angle of theta with respect to the horizontal plane. Then in Mohr circle, we have to rotate this point by an angle of 2 theta. So this is known as double angle approach. Normally we measure with respect to this point because we consider theta with respect to the horizontal plane. If we consider theta with respect to the vertical plane, then we will consider this stress. But for geotechnical problem, we will consider theta with respect to the horizontal plane. So this will be theta, and for double angle approach, we have to actually rotate the point by 2 theta. In place of this rotating by 2 theta, this thing is actually a little bit difficult because we have to measure the 2 theta again and again. We have to measure the 2 theta, and this is actually difficult. In place of this, one very important concept is there, which is the concept of pole. In pole, actually what we do, this stress is actually the stress corresponding to the vertical plane. Sorry, this is sigma x minus tau xy, and this is sigma y minus tau xy. Sigma x tau xy, sorry, this is sigma x tau xy, and this is sigma y minus tau xy. So this plane is actually the plane corresponding to the horizontal plane, and this stress is the stress corresponding to the vertical plane. So this is the stress sigma x tau xy, sigma x tau xy. This is the point. This point is actually the stress corresponding to the vertical plane. This is the vertical plane. This is positive tau xy because I have already mentioned that it is creating anti-clockwise movement, so it is positive. And this particular point, this point is the point with respect to the horizontal plane, sigma y and minus tau xy, and minus tau xy because this tau xy is actually creating clockwise movement, so that's why this is minus tau xy. Now this plane is the plane of vertical plane. This point is the stress corresponding to the vertical plane, and this stress is actually stress corresponding to the horizontal plane. So what we will do actually, we will draw the line, one line parallel to the vertical plane. This is vertical stress, so we will draw one line parallel to the vertical plane. This is horizontal stress, so we will draw one line parallel to the horizontal plane. So these two lines will cut the Mohr circle in this particular point. These two lines will cut the Mohr circle in this particular point, and this point will be termed as pole. Pole is actually the origin of the plane. This pole is very important. If we know the pole, then actually calculating the stress is very easy. If we know the pole, then actually, suppose we want to calculate the stress for a particular angle, for a particular plane, which is at an angle of theta with respect to the horizontal plane. So this is the plane for which we want to calculate the stress. So what we will do, we will just draw one line parallel to this particular plane. We will draw one line parallel to this particular plane, and this particular line will cut the Mohr circle in this particular point. And from this point actually, measuring the value of normal and shear stress, we will get the value of sigma n and tau nt. By rotating 2 theta we can get the value, or by just if we just create the pole, from pole, if we draw the line parallel to the plane, if we just draw one line parallel to the plane, then we will get the value of, then we will also get the value of normal and shear stress. So both these concepts are important, but actually pole approach is more useful. And for mathematics also, we know actually this particular angle is actually known as inscribed angle in geometry. we know that inscribed angle is actually inscribed angle is the central angle is actually double of the inscribed angle. If this is theta, it will be 2 theta. The central angle is always twice the inscribed angle if the arc is same. If for the same arc, the inscribed angle will be actually the half of the central angle. Central angle will be double of inscribed angle. So this is the concept. So we can use both the approach, but why pole approach is very important? Because for pole approach, suppose we know that this is the pole, and this is the point of minor principal stress. This is the point of major principal stress. This is the point of major principal stress. So if we just connect pole with these 2 points, if we just connect the pole with these 2 points, then actually this is the plane of major principal stress, this is the plane of major principal stress, and this will be the plane of minor principal stress. Because from pole we are connecting the minor principal stress from pole with this line. So if we just draw one line parallel to this particular line, then we will get the plane for minor principal stress. So this will be the plane of minor principal stress, and we are connecting the pole with the major principal stress by this line. So if we just draw one line parallel to this line, then we will get this is the plane of major, and this will be the plane of minor. So from pole actually we will get the value. Suppose we want to know the plane for maximum shear and minimum shear, we have to just connect pole with these 2 points. And then if we just draw the line parallel to this particular line, then this will be the plane of maximum shear, because actually this line is actually connecting the pole with the point of maximum shear. So this will be the tau max, the plane of tau max, because this line is parallel of this line, and this line is parallel of this line. Pole is connecting with this particular minimum tau mean with this line. So if we just draw the parallel line, then it will be the plane of tau mean. So this will be the plane. If we just know the pole, then we can easily identify the plane with maximum shear, minimum shear. So this is the concept. Now for soil, actually soil generally fails in shear. Suppose this is one steep footing. When there will be increase in load, this particular footing will give pressure in this particular direction to the soil, and it will actually push the soil to move in this direction. So some resistance will be there. From soil surface there will be some resistance, and obviously the resistance will be in the opposite direction. Same for one particular embankment actually. If there is some slope, then due to the self weight of soil, it will try to move in this direction. But there will be some resistance from the soil itself. There will be some resistance, and the resistance will actually act in the opposite direction. So this is the failure surface. If there is some failure due to steep footing or due to embankment, then this will be actually the failure surface. And when there will be failure, the shear stress will actually achieve the shear strength. Shear stress is tau. Shear strength is actually the maximum value. Maximum value means maximum value that the soil sample can actually take. And normally soil fails in shear. For soil, the most critical thing is actually shear. So when the shear stress will go in the maximum value, at that time there will be failure. And that particular condition, that is known as shear strength. This is shear strength. Shear strength is actually the maximum shear stress that the sample can take. So these are the two conditions. Of movement of soil. So this is the movement of soil. Here you can see also. For these two conditions, there is some movement in soil. So these are actually shear failure. Of soil. So this is the condition of slope. Here actually you can see that soil is moving in this direction. So there will be some resistance. There will be some shear resistance, and this will be the failure surface. The soil grain will actually slide over each other. Soil grain to soil grain will actually slide over each other. and when it will slide over each other, then there will be failure, and this will be the failure plane. This will be the failure plane. No crushing of the individual grain. This grain will actually, there will be no failure. This soil grain will be there, but one will actually slide over the other. Like wheel, we can think that this soil grain will actually move in this direction, and this will move in the opposite direction. So this, there will be shear failure. Shear failure, and this will be the direction of shear stress, and this will be the direction of normal stress. Shear stress and normal stress. Normal stress is compressive. As I have mentioned before, that normal stress will be compressive for geotechnical problem. Failure will occur when shear stress will reach the shear strength. Shear strength is the maximum shear stress that the soil sample can actually take. So tau f is actually the maximum value. When the shear stress will achieve the maximum value, at that time there will be failure. Now Mohr-Coulomb failure criteria. Mohr-Coulomb failure criteria is very important. There is one failure envelope. There is one failure envelope. If our Mohr circle touches that failure envelope, at that time there will be failure. When the Mohr circle will touch the failure envelope, at that time there will be failure. Normally for geotechnical problem, one thing we have to actually remember, that actually Mohr circle is normally symmetrical with respect to the y-axis. At the upward direction and downward direction, both are actually same. So normally what we do, normally we consider only the upward direction. We do not just draw in the downward direction, we just do not draw it. But this will be the Mohr-Coulomb failure criterion. If the Mohr circle touches this particular line, then there will be failure. It will be similar in the downward direction also. In the downward direction also there will be failure envelope, but we do not draw it. We do not draw it, we just draw in the upward direction. We just draw the half. So when the Mohr circle will touch this particular line, then there will be failure. Like different type of failure theory, we know that when a particular Mohr circle, when the stress actually achieve the maximum value, when it will touch the envelope, at that time there will be failure. So first we have to know about the failure envelope. This is the equation of failure envelope. Tau f equals to C plus sigma tan phi. C and phi are measures of shear strength. C measures the cohesion. C measures the cohesion of soil, and phi is actually the angle of internal friction. Angle of internal friction. Now actually, if the soil is cohesive soil, then there will be the value of C. And if the soil is cohesion-less soil, if it is a normal cohesion-less soil like granular soil, for which there is no cohesion in between these 2 points, normal sand, when there is no cohesion, at that time there will be phi value. But normally for a particular condition, there can be both C and phi. C measures the cohesion, phi measures the angle of internal friction. Now for a particular soil which is cohesive, for cohesive soil there will be C. For cohesive soil, it can be this particular failure envelope can look like this. If it is a total cohesive soil, then C will be there. And for a particular soil, if it is cohesion-less soil, means there is no cohesion at all, normal sand, at that time the graph will look like this, because C will be 0. This particular equation is actually very similar to y equals to mx plus c. We know that m is actually the slope and c is actually this particular value. This is actually the c, and m is the slope, tan theta. So this value is the c, and this value is actually our sigma tan phi, and this is sigma. This is sigma, and this particular angle is phi. So for a cohesive soil, if phi is 0, then it will be horizontal, the line will be horizontal if phi is 0. And if c is 0, then the line will actually touch the line will go through the origin of the particular graph. If c is 0, then the line will look like this. If phi is 0, then the line will look like this. But for a particular soil, if both c and phi is there, then it will look like this. Both property of c and phi will be there. And c phi both actually measures the shear strength. C and phi both actually measures the shear strength. And higher the value, higher the shear strength. If c and phi both are actually more for a particular soil, then its shear resistance will be more. shear strength will be more. Now this is one very important thing. This is the Mohr circle and failure envelope. Like for a particular condition, I am just saying that suppose there is some soil in a particular height of Z. There is a soil sample which is at a height of Z from the ground surface. Then the horizontal stress and vertical stress will be something like this. The vertical stress will be gamma Z. We know that the vertical stress will be gamma into Z. Gamma is actually the unit weight of soil. This equation is very similar to rho g h. Rho is the density, g is the acceleration due to gravity. So rho g is actually the unit weight, density into g. So this will be the unit weight into h. So this is actually the gamma z is actually the vertical stress, and horizontal stress at rest will be k0 into gamma z. Horizontal stress at rest will be k0 into gamma z. Normally k0 is less than 1. And there are different equations for calculating k0. Normally k0 will be less than 1. So actually vertical stress is actually greater than the horizontal stress. So if we just draw the Mohr circle of one particular point, this y point, then the Mohr circle will be something like this. This is the Mohr circle. And this will be the point of sigma h or sigma v. This is the point. Which one is less? Vertical stress is gamma z, horizontal stress is k0 gamma z. So obviously for geotechnical problem, for normal problem of soil at rest condition, this will be sigma h, this will be sigma v, because sigma v is actually more than the sigma h. Now for this y point, this is the condition. But for one particular point x, for this point, normal stress in the horizontal direction and in the vertical direction is such that it is touching the Mohr circle. And when it will touch the Mohr circle, at that time there will be failure. So this particular point is actually critical point. For this point actually there can be failure. If a point is over this x point, suppose there is a point here, then actually for this point the z value is very less. So for this point both the vertical and horizontal stress both will be very much less. So this particular Mohr circle can be here. Obviously it will be over the failure envelope. So it will fail. All this point here over this failure plane, if we just draw the Mohr circle will actually cut the failure envelope. But if a point is safe, suppose here there is one point here. For this point both vertical and horizontal stress is very high. So for that point the Mohr circle will be somewhere here or here. The more deep we go, if we go for a more deeper point, at that time the Mohr circle will actually move towards the right. So there will be no failure. When it will touch the failure envelope, at that time there will be failure. So this is the very important thing. So suppose there is one particular this is one particular point with vertical stress sigma v and horizontal stress sigma h. Obviously sigma v is greater than sigma h. Sigma v is gamma z, sigma h is k0 gamma z. At rest condition sigma h is less than sigma v. So the Mohr circle will look like this. Now suppose we increase the weight, we just add some weight. Here we have added some weight. So when we will add some weight, the horizontal stress is suppose same, the vertical stress is actually increasing. We are increasing the weight, so the Mohr circle will look like this. And sigma v will actually shift by certain amount of sigma v plus del sigma. Del sigma is actually the stress due to this increase in the weight. We have increased the weight, and due to this weight the vertical stress actually increased by certain amount. And as the vertical stress increased by certain amount, so the Mohr circle will actually increase. Now when we will increase the weight, if we just start increasing the weight one by one, this is the Mohr circle. Initially this is the Mohr circle. After we increase the stress, then this is the Mohr circle. Now if we just start increasing the weight one by one, then Mohr circle will start shifting towards the right. And one particular time will come when the Mohr circle will actually touch the failure envelope. And when the Mohr circle will touch the failure envelope, at that time there will be failure. When Mohr circle will touch the failure envelope, at that time there will be failure. So this is the condition of failure. This is the condition of failure, when Mohr circle will touch the failure envelope. As loading progresses, Mohr circle becomes larger, and finally failure occurs when Mohr circle touches the failure envelope. So when Mohr circle will touch the failure envelope, at that time there will be failure. Now one another thing is very important actually. What is the plane of failure? Which one will be the plane of failure? That thing is very important. And at that time actually the concept of pole will become very important. The concept of pole will become very important. Like for the failure condition, this is the horizontal stress and this is the increased vertical stress. So this particular point is the point with respect to the horizontal stress, and this particular point is point with respect to the vertical stress. So this is the point with respect to the vertical stress, and this is the point with respect to the horizontal stress. Now horizontal stress actually acts in the vertical plane. Horizontal stress sigma h actually acts in the vertical plane, and vertical stress sigma v plus del sigma, this actually acts in the horizontal plane. So this is the stress corresponding to the vertical plane, and this is the stress corresponding to the horizontal plane. Stress is vertical but acting on the horizontal plane. This stress is horizontal but acting on the vertical plane. So what we do when we try to construct the pole? This is the vertical plane, so we will draw one vertical line, and this is the horizontal plane, so we will draw one horizontal line. This two particular line is cutting the Mohr circle in this particular point. This two particular line is cutting the Mohr circle in this particular point. So this is actually the pole. This is actually the pole, and this is the pole. So from pole, if we just draw the line, then we will get the failure plane. Now, which point is the point corresponding to the failure point? For this point, for Mohr circle, this particular point is actually cutting the Mohr circle. When Mohr circle was increased, then this was the point. This is the point where Mohr circle is actually cutting the failure envelope. For this point, Mohr circle is actually touching the failure envelope. So this is the stress corresponding to the failure point. For the failure plane, this will be the stress. So for failure plane, this will be the normal stress, and this will be the shear stress. This will be the shear stress. And this shear stress is actually lower than the tau max. Tau max is more. But for a lower value of tau, actually the failure has occurred. Now this is the pole, and this is the point with the failure stress. For this point, failure has occurred. So if we just connect the pole with respect to this point, then this will be the failure plane. This will be the failure plane. And this particular angle is phi. This particular angle is phi. So if we just draw a triangle, this is phi, this is 90 degree. So it will be 90 degree plus phi. So this particular angle, this angle will be 45 degree plus phi by 2. Half of 90 degree plus phi. This is central angle, this is inscribed angle. So this will be 45 degree plus phi by 2. So this will be the failure plane with respect to the horizontal. With respect to the horizontal plane, this angle, this will be 45 degree plus phi by 2. And the value of stress will be this. From this particular point, we will get the value of shear stress over this particular point. So this is the concept. Now if we go for a particular problem with Mohr circle, then it will be easier for you to understand. Suppose a specimen of clean, dry, cohesionless sand is tested in a direct shear box. The soil fails when the shear stress on the failure plane reaches 40 Newton per meter square, while the corresponding normal stress on the specimen is 50 Newton per meter square. So the normal stress is 50, and we have applied one shear stress. Normal stress is 50, and we have applied one shear stress like this. That value is 40. When the shear stress is 40, at that time failure occurred in this particular plane. In this horizontal plane, failure has occurred in the direct shear box. So this is the concept. Now we have to measure all the value. We have to measure the angle of internal friction phi. We have to measure the major and minor principal stress. Major and minor principal stress and angle. So how to do that? Stress and their angle. So how to do that? By Mohr-Circle, by using Mohr-Circle, we can do it very easily. We can do it very easily in Mohr-Circle. Like in x-axis we will put normal stress, in y-axis there will be shear stress. Now first we will actually draw this is suppose this is 10, 20, 30 like this. So we have to first draw the point for which the normal value will be 50 and shear value will be 40. So this point will be 50, 40 because normal stress applied is 50 and shear stress applied is 40. So this point will be 50, 40. And for this point actually failure occurred. For this point failure occurred. So this point is actually over the failure envelope. So if we draw the failure envelope, then this point will be actually over the failure envelope. And this soil is actually cohesionless soil. So as the soil is cohesionless soil, so C is actually 0. C is 0. And if we measure this particular angle, if we just measure this particular angle, then we will get the value of, actually get the value of phi. So how much will be phi? Phi will be tan phi is actually height by base. So height is how much? Height is actually 40, base is 50. So phi will be tan inverse 4 by 5. Tan inverse 4 by 5. So it will be 38.7 degree. 38.7 degree. So this is the failure envelope. Now we have to draw the Mohr-Circle. We do not have any other data. So we have to draw the Mohr-Circle. So what we will do? We will draw one line perpendicular from this particular point. From this particular point, we will draw one line which is perpendicular to the failure envelope. So this angle is 90 degree. This particular point will be the point center of the Mohr-Circle. So now if we take this as the center and if we take this particular line as the radius of the Mohr-Circle, then we will get this particular Mohr-Circle. This will be the Mohr-Circle. This will be our Mohr-Circle. Now from Mohr-Circle we can actually calculate the major principal stress. This will be almost 132. The minor principal stress, this is almost 31. So major or minor we have already calculated. This is 132 and 31. Major is 132, minor is 31. Now what is the failure plane? Failure plane is actually this plane. Here actually the failure has occurred. Due to the load, here actually failure occurred. So failure plane is actually horizontal plane. So horizontal plane is actually the failure plane. Now we have to actually identify the pole. Pole thing is very important. Like we know that this is the failure point. This is the failure point. And from failure point, if we draw the failure plane, from the failure point, if we draw the failure plane, then this point will be our pole. This point will be our pole, because we know that from pole, if we connect the stress, from pole, if we connect the stress, then we will get the plane. So if this is the plane, we already know the failure has occurred in a horizontal plane. So if we just draw the plane, then we will get the pole. So this is the pole. So minor principal stress is 31, major is 132. So we know the value from the Mohr-Circle. If we just connect these 2 points with the pole, then we will get the plane with respect to the, this is the plane. If we just draw one particular plane parallel to this line, then this particular, this is the plane of minor. And if we just draw one plane parallel to this line, because this is connecting pole with the major. So if we just draw one line parallel to this particular line, then this will be the plane of major principal stress. Major principal stress. And how much will be the angle? This angle is almost 65 degree. And this angle is almost 25 degree. So we know that what is the angle with respect to horizontal, how much is the angle, that we can easily actually calculate. We know this angle is 65 degree. So this is 65 degree. This angle will be 65 degree. And this angle is actually 25 degree. This is 25 degree. So this is the concept. This is the concept of pole. And suppose this is another problem. This problem is also very interesting. Like a saturated cylindrical specimen of clean cohesionless soil was tested in a consolidated drain triaxial compression test. Cohesionless soil, this is very important. The specimen failed when the deviator stress reached 3 kgA per centimeter square under a cell pressure of 1 kgA per centimeter square. So deviatoric stress is 3 and cell pressure is 1. That means for triaxial test we actually give one cell pressure. From all direction we actually give one cell pressure, that is actually 1. After that we actually increase the deviatoric stress. Deviatoric stress is actually 3. Deviatoric stress is actually given in the vertical direction, that value is 3. So 1 plus 3, so the vertical stress will be 4. Vertical stress will be 4 and the horizontal stress will be 1. 4 and 1. Deviatoric stress plus cell pressure, that will be the vertical stress. So this is the stress condition, and in this stress condition failure occurred. So we have to measure the effective angle of shearing resistance, we have to measure the phi value, major and minor principal stress at failure, the orientation of the failure plane with respect to the major principal plane and this is minor principal plane. Major principal plane and major principal stress direction. So that we will actually calculate. Now we have to draw the Mohr circle. Along x-axis there will be sigma, along y-axis there will be tau. Now actually this soil is actually cohesionless soil. So for cohesionless soil, C will be 0. So the failure envelope will look like this. And this will be the Mohr circle. This will be our Mohr circle. This value will be 1 and this value is 4. This is the vertical stress, this is the horizontal stress. So this is 1, this is 4. And failure occurred. So obviously this particular Mohr circle will actually cut the failure envelope. Mohr circle will touch the failure envelope as failure occurred. So this is the condition. Now we have to calculate, we have to measure the angle, we have to measure the phi. So how to measure the phi? This is the center of the Mohr circle. So if we just connect, this particular failure envelope is actually tangent with respect to the Mohr circle. So if we just connect these two lines, then it will be 90 degree. So now if we just think about this triangle, suppose this is O, suppose this is A, B, C, D. So if we think about this triangle, this angle is 90 degree and this is phi. So how much will be sin phi? Sin phi will be height by hypotenuse. Sin phi will be height by hypotenuse. So how much is the height? Height is actually the opposite of phi. This is the height and this is the hypotenuse. As this angle is 90 degree, so this is the hypotenuse. So how much will be the value of OC? OC will be how much? For A point the coordinate is 10, for B point it is 40. C is actually in between A and B. So obviously it will be 2.50. For C point the coordinate is 2.50. So obviously OC is actually 2.5. This is 2.5. And how much is CD? CD is actually the radius of the Mohr circle, and the radius of Mohr circle is actually, this value is actually 1.5. Total gap is 3. So radius is 1.5, 1.5. So this is also 1.5. So how much will be sin theta? Sin phi? Sin phi will be 1.5 by 2.5. This is 1.5, 2.5. Height by hypotenuse. So this will be 3 by 5. So phi will be how much? Phi will be sin inverse 3 by 5. Sin inverse 3 by 5. So it will be 36.87 degree. So phi is actually 36.87 degree. Phi is actually 36.87 degree. So this is the value of phi. Now we have to also measure the plane for major and minor principal stress. So this point, this is actually 10. This is actually the this particular case. This is 10. Horizontal stress, this is 1. So horizontal stress is corresponding to the vertical plane. Horizontal stress is corresponding to the vertical plane, and vertical stress is 4. This is 4, and 4 is this 4 is actually corresponding to the horizontal plane. So from 4, if we just draw one horizontal line, because for 4 this 4 stress is corresponding to the horizontal plane. So from 4 we will draw one horizontal line, and from 1 we will draw one vertical line. 1 is corresponding to the vertical plane. So from 1 we will draw one vertical line. So these two are actually connecting in this particular point. So this is our pole. This is our pole. This particular point is our pole. So if we just connect these 2 points, D and A, if we just connect these 2 points, this will be our failure plane. Failure plane. This will be our failure plane. AD will be our failure plane. And how much will be the angle? This is phi. This is 90 degrees, so it will be 90 degree plus phi. The central angle is 90 degree plus phi. So this is the inscribed angle. It will be half, 45 degree plus phi by 2. So failure plane will be 45 degree plus phi by 2. So it will be 45 degree plus phi is our 36.87. So it will be 63.43. So it will be 63.43 with horizontal. So failure plane, this particular angle, this angle will be 63.47 degree. So this is the angle of the failure plane. This is the angle of the failure plane. This is the pole. This is the pole. So if we just connect these two lines, this will be the failure plane. This will be the failure plane. So this is the concept. If we just construct the Mohr circle will actually give us the idea of all this value. If we just can draw the Mohr circle, then from Mohr circle we will get every value. And this will be the stress. For failure condition, this will be our stress. So this is all. Hope you have able to understand that how we can use the Mohr circle in calculating the shear strength of soil. Thank you for your attention. If you have any type of question, you may ask that in the comment box. Thank you.